Okay, we're going to now progress to looking at internal energy, enthalpy, and specific heats of solids and liquids. Let's look at an incompressible substance. In a substance whose specific volume or density is constant is an incompressible substance. And often, solids and liquids can be approximated as incompressible substances. So what we're going to go ahead and we can show that for solids and liquids, you can often make the approximation that specific heats at constant pressure and constant volume just basically equate to one value, which is a specific heat, right? We're not going to assume specific heat, constant volume, or constant pressure. It is the same thing. So, as it was for ideal gases, one can also show that the specific heat of an incompressible substance is a function of temperature only. So again, Cp and Cv are approximately the same, called specific heat, and we can also assume that the change in internal energy, right, U2 minus U1, is basically equivalent to is equated to the integration of that specific heat as a function of temperature over temperature, and you can approximate it as a average CV. If you assume it to be constant with specific heat, constant with temperature, you can assume this one specific heat value over the temperature range, and the integral results in C delta T. Now, what about for enthalpy changes? Right? We just went ahead and we said for internal energy, but what about for enthalpy changes? If you recall, the definition of enthalpy is internal energy plus pressure times specific volume. Let's go ahead and let's take that and let's differentiate it, right? So we get dH is equal to du, and then we need to apply the chain rule because both P and V are variables, right? So P dV plus, sorry, P d nu plus nu dP. Now, if my substance is incompressible, the volume is constant, right? So specific heat, the change of specific heat is 0. So d nu volume, or d nu is 0. So we end up with, if I go ahead now and integrate, I get that delta H is equal to delta U plus nu delta P. Now for solids, nu delta P is often insignificant. So for solids, we get that delta U is equal to delta H. Now for liquids, there's two basic assumptions. One, for a constant pressure process, right, this becomes 0, so you're left with delta H equals delta U. For a constant temperature process, you're left with delta U to be 0, so delta H is equal to nu delta P. Again, this isn't anything, this is all based on assumptions, starting with the basic definition of enthalpy, differentiating it, and then making assumptions based on whether it is a solid or a liquid. Let's go ahead and let's do an example problem. In this problem, we have stainless steel ball bearings, each have a diameter of 1.2 centimeters, are being quenched, they are to be quenched in water at a rate of 800 bearings per minute. The bearings leave the oven at a uniform temperature of 900 degrees Celsius and are exposed to the air, which is at 25 degrees Celsius. So they basically are exposed to the air for a while, and then they drop into the water when they are at 850 degrees Celsius. So it's asking you to determine the rate of heat transfer from the bearings to the air. Right, so I'm going to go ahead. My schematic. Just basically, I have here a surface. I'm going to assume here's an oven, and out of the oven come ball bearings. Ball bearings flow out, eventually falling into, not falling, but being quenched into water. They're 850 when they get to the point of being immersed in the water, and they're at 900 when they come out of the oven, and the ambient temperature is at 25 degrees Celsius. So I have Fahrenheit here. I meant to put Celsius. Now, to draw some assumptions, right, we could draw several assumptions. Number one, I'm going to assume the bearings are solid. Number two, I'm going to assume the change in kinetic and potential energy of the system is 0. This is for delta E system. 3, I'm going to assume the temperature of the bearings is uniform. And I'm going to assume the bearings are a closed system. And I'm also going to assume specific heats are constant, so they're not a function of temperature. So let's go ahead and let's try to solve this problem. Like any first law analysis, we start by writing the compact form of the first law. E in minus E out equals delta E system. Now what we're doing is we're doing a first law analysis on the balls as they are rolling, as they are going, right? So I don't have any energy by mass entering the balls, nor by heat, nor by work, right? So the moment they enter the oven, they're actually losing heat in the environment. So the only energy exchange going on is heat leaving the ball bearings. And the change in energy of the system is going to be equated to the change in internal energy, plus the change in potential energy, plus the change in kinetic energy. Assuming the change in kinetic energy and the change in potential energy is 0, I'm left with the change in internal energy. With it being a closed system, the masses are constant, so the result would be mass times U2 minus U1. Bringing the minus sign to the other side of the equation, I get that the heat loss from the ball bearings is equal to mass times U1 minus U2. Now, assuming constant specific heats for this solid, I'm going to go ahead and I'm going to factor out my specific heat, and I will approximate delta U as C delta T. You see how all these assumptions, this to this is based on assumption number 2. Factoring out the mass is assuming it to be a closed system, which is assumption number 4. Equating delta U as C delta T is assuming constant specific heats, which is assumption number 5. Right, do you kind of see how the assumptions work and being able to evaluate your first law analysis step by step? I'm using the assumptions in order to specify this first law for this particular problem set. Now the only thing is to go ahead and evaluate the rate of heat loss. Right, the rate of heat loss will be basically equated. I got to first find the mass of a ball. Right, the mass of the ball. So if I first look at a volume of a ball bearing, it's spherical. So the volume of a spherical object is 4/3 pi r cubed. Right, so in the problem, they give you, do they give you anything being able to find the volume? Yes, here it is. We have the diameter is 1.2 cubic centimeters. So with that diameter, you can find the volume. And you know the mass is going to be the density times the volume. Right, again, the problem statement gives you density of the ball bearings, which is 8,085 kilograms per cubic meter. Filling those numbers in, you should find that each ball has a mass of 0.1756 kilograms. Right, and that is per bearing or per ball. So with that said, my mass is going to be 0.1756, and again, that's kilograms per ball bearing. Now, the problem statement also is telling us that the flow of the balls is 800, right? We have 800 balls per minute. Then we have, of course, there is in 1 minute, there is 60 seconds. That all multiplied by the specific heat, which is given in the problem statement as 0.480 kilojoules per kilogram Kelvin. Kilojoules per kilogram, kilogram Celsius, kilogram Kelvin, it's the same thing. Multiplied by the difference in the temperature change, which would be 900 C coming out of the oven and 850 C before it gets quenched. You plug in all these numbers and you should get the total heat rate. The rate of heat transfer ends up being 2.34 kilowatts. 2.34 kilowatts.